Can you hear me, Akshay?
Yes, sir, I can.
I think something going wrong in my... Can you speak?
Can you
Your
hear me?
micro... Yes, I can hear you. Is a speaker there?
Not yet, sir.
I think he's there. I think the speaker, Paul,
Yes,
Dr. Paul has
I'm
joined.
just making him up.
Hi, Paul. Can you hear me?
Hi, can you hear me now?
Yes, thank you so much. Good morning, Paul.
Great.
How are you?
Good morning.
Yeah, thank you so much for agreeing to do this talk. We appreciate your time.
Sure. Yeah, likewise. Thank you for having me.
Yeah. So just to give you a quick overview, we've been doing this webinar for the last 2 years. We received good reception, and we also have populated so far about 80 plus videos and every week, and we're doing on cyber. And it's also hosted on multiple other universities. So I would appreciate maybe we can also try to, in future, we can promote this at your university too, maybe
Okay.
to your students or your group, or maybe a computer science department over there. And I can add the logo for your university there, so we can say jointly hosted,
Mm-hmm.
Great. And I think the webinar is about 45 minutes or 50 minutes, and then we can have 10 minutes for Q&A. Do you mind sharing your screen to see if it works, to make sure
Yes,
that...
let's do that. Yeah. And so you said 45 minutes for the talk?
45 to 50 minutes, yeah.
45 to 50. Okay. Yeah, I wasn't sure. So yeah, the timing was like 30 to 45, so I wasn't sure whether to include.
Yeah, it's fine. And depending on
some
however
content.
long, yeah, we can restrict to 40, 45 minutes if you think that's also
Yeah, I can see how it goes. It depends on, I have extra content if need be. Okay, let me make sure that sharing works. So let me, it says I can't share while the other participant is sharing.
Akshay, could you try what's going on?
I think, yeah, okay. There was other previous screen sharing. Okay, let me.
The weather in South Florida must be hot, huh?
It's nice. It's in the 70s, so it's pretty good.
It's
Are you
35.
able to see my screen?
Yes. Yeah, we're good. Yeah. This is cool.
Okay.
Yeah.
Okay.
And now, Jamison or Akshay, can you share the speaker's bio so I can introduce the speaker in a few minutes? Oh, it's already time, so we should introduce. Can you share the screen?
Would you like me to stop sharing?
Yes, please.
Okay. Oh, okay. There we go.
Okay. Good morning, everyone, for this distinguished webinar series in AI and cyber. Today's speaker is Dr. Paul Gazzillo. The title for today's talk is Beyond the Programming Language, Bringing Analysis and Testing to the Entire Software Ecosystem. Dr. Paul is an assistant professor of computer science at University of Central Florida. He received his Ph.D. from NYU and previously worked as a postdoc at Yale and a research scholar at Stevens Institute. His research aims to make it easier to develop safe and secure software, and it spans program analysis, software engineering, and security. Projects include analysis of configurable software, software supply chain security, and corporate entity tracking. His work has been published in numerous avenues such as ICSE, ESEC/FSC, and PLDI, and has been recognized with the DARPA Young Faculty Award, an NSF CAREER Award, and ACM SIGPLAN Research Highlight. Dr. Paul, it's a great pleasure and honor to have you at the UND's distinguished webinar series. We appreciate your time, and the floor is yours.
Thank you very much. Let me share my screen. All right. Are you able to see my screen?
Yes.
All right. So thank you so much for the introduction. I'm very excited to be here. And so, as was introduced, my talk is Beyond the Programming Language, Bringing Analysis and Testing to the Entire Software Ecosystem. And so just to kind of put a little bit of a box around this, the overall vision of the set of projects in my lab over the past couple of years has been to take some of the successes that software analysis has had on code and expand this to the entire software ecosystem so that we can have stronger and better, more secure software. So let me put this into context a little bit. So in the current landscape of software security and vulnerabilities, memory safety dominates the world of exploits. So this is the top 10 actual known exploited vulnerabilities from the CWE Common Weaknesses database. And memory safety dominates. And so these are your classic buffer overflows, buffer overreads, stack smashing attacks. These are still very, very prevalent and being found at a good clip in real software. The origin of these bugs is C and C++. If you look at all of these weaknesses, they're just in C and C++. And that's because most of the critical software that we rely on, or a very large part of it, tens or hundreds of millions of lines of code, is still written in C. And so this problem of memory safety is still kind of nipping at us and causing security vulnerabilities. But the memory safety problem is I would argue, solved already for several decades. So there was a memory safe version of C called Cyclone from a couple days ago. Java, or a couple decades ago, Java was introduced to avoid memory safety issues. And now we have all of these options for not just detecting memory safety problems, but really programming in a way that virtually eliminates the kinds of very frequent memory safety issues that we've seen over the many past decades. And so currently the scope of exploits is still memory safety still dominates, but in the computing world, in the computer science world, the problem is arguably solved already. And so it's really just a matter of time before these kinds of memory safety issues become lower down the scale, I argue, of commonly exploited vulnerability. So as software gets ported to safer languages and as safer programming practices get introduced. And so I argue this is just a matter of time. There was actually a press release just this week from the White House about memory safety in software. So this is getting kind of national, non-technical attention. And of course, we had these several languages, Rust, Go, and Swift, which are candidates to kind of replace C for systems programming. And there are real efforts to actually deploy these in the wild. So Rust for Linux is a project that added support for writing parts of the kernel in Rust, and it's memory safe Rust language. Apple has adopted Swift for their iOS development. And so even though memory safety is still dominating, from the computer science point of view, we want to look forward in the future and see, well, we think this is going to go away at some point. But what's left? Are attackers just going to stop trying? Probably not. So this is the kind of DevOps view of the phases of software development. You could pick any software development lifecycle. You've got coding, deployment, testing, monitoring the live system, and the actual software engineering paradigm doesn't really matter here. But the point here is that memory bugs happen in coding. They're really just implementation bugs. And so attackers are depending on developers to make these mistakes. But as these mistakes become much harder to make, well, these are going to be less of a target for exploiters and vulnerabilities. And so what's left if these memory-based attacks go away? Well, we have the entire software development lifecycle that is vulnerable to attack and is an opening for other kinds of attacks. And this is not just theoretical. There's been several recent high-profile attacks on software that does not need any particular bug in that software to exist. So for instance, the SolarWinds Orion attack led to hundreds of organizations being owned effectively by attackers, including many agencies of the US government. And this attack was a little, very, very clever. Instead of trying to find vulnerabilities in the software and implementation bugs, they just sidestepped the challenge of doing that and instead infected the build system. They infected the code that makes the software. And so you had this malware being deployed in developer-signed software from this company that serves a huge amount of organizations and intelligence services. And so they were able to get malware into signed code without even having to break the software. Instead, they broke in to the people developing it, and they broke into the so-called software supply chain or the software operations in order to insert malware. We also had the log4j vulnerability, the log4 shell vulnerability. And if you'd seen this one, this is logging software that's used in an enormous number of Java applications. And it's just a kind of, lowly, trustworthy logging solution that helps you just do what good programmers are supposed to do. You're supposed to log your errors, have good information. But there was a feature in here that effectively allowed remote code execution. And I call this a feature and not a bug because it was intentionally added, and it was something you could actually disable with a configuration setting. You could just go into your settings for log4j and say, well, I don't want this functionality. And that was actually the solution, one of the solutions to avoiding this vulnerability. But because by default this was turned on, it became, quote, one of the most critical vulnerabilities, at least according to some sources, up to this point in history, where an enormous amount of code was vulnerable, an enormous amount of organization, an enormous amount of projects, because they depended on log4j. So log4j was not an application, but it was part of the software supply chain, part of the ecosystem of developing software. And when attackers discovered and publicized an attack in that, well, now all this other software that could be implemented perfectly, it could have zero memory safety bugs, zero implementation bugs. Now that you depend on this piece of software that has a feature that is not very desirable, that you probably should turn off, well, now your software is vulnerable because of this third-party software that has this feature that we didn't really think would be attacked. And this notion of attacking the stuff around the software instead of kind of directly breaking in, this is not a new notion. So in the 80s, Ken Thompson, one of the original Unix guys who helped develop the Unix operating system and C, gave a Turing Award lecture that was kind of unique. It was not about anything about Unix or anything like this. It was called Reflections on Trusting Trust. And he outlined a way in which the compiler could insert vulnerabilities into software. And taking it a step further, he pointed out that even if you checked the compiler, you could actually hide a vulnerability in the compiler in such a way that even if you looked at the source code of the compiler, you wouldn't even see this vulnerability. And so this really brings home the point that it's not just about breaking software or breaking in. If all of the ecosystem around it is not safe, then it doesn't matter how correctly written your software is. And so this is kind of a, going back thousands of years, this is a classic kind of Trojan horse attack. So why bother breaking into the bank vault when you can just, steal the keys of the custodian or steal the keys of the bank manager and get in without having to do any kind of fancy technical attack. And so to bring it back to the vision of what our lab is working on, is we're trying to take all of the great work that's been done on looking at software vulnerabilities in code itself and apply this kind of this idea of automatically identifying these kind of vulnerabilities, but bring it to the whole software ecosystem. And now that's a big vision. I won't even pretend that we're solving all of these problems. We're just scratching the surface. But what we've been doing, and what I want to show you today, is that we've been starting small. We've been looking at another piece of this software ecosystem. We've been looking at the build system, the next step after coding. And we've been exploring several different ways to defend against these kinds of attacks and provide foundational tools that will allow automated analyses to identify and protect these parts of the software ecosystem against attacks. Okay, so let me zoom in now a little bit on one piece of this software ecosystem. Let's look at the build system. And I'd like to take a look at the Linux kernel build system. And so the reason we chose the Linux kernel build system is, one, it's open source, so we actually have access to it. But two, it's also huge. It's like 20 million lines of code is the kernel itself. And because it's just used in so many places, its build system is like 200,000 lines of code. Its build system itself is like a medium-sized software project. And so this kind of illustrates what the future pitfalls or what the future vulnerabilities are going to be in software when all of the automation and operations around the software become really software products in their own right, but don't have this kind of rigorous understanding of the behavior of these systems that code has because of decades of research on understanding how code works and how code breaks. And so the Linux kernel is a good model for us because, yeah, it's open source and it's used widely. So it's 70% of mobile devices, 70% of IoT developers use it. It's in a plurality of servers around the world. And part of the reason that the Linux kernel is so widespread, or what allows it to be so widespread, is that it's extremely configurable. You can, you probably read articles of people installing the kernel on like a toaster or a refrigerator. It's so configurable that you can really target just about any piece of hardware that you want. And the reason for that is not so much code in C itself, but it's really its build system, its build and configuration system. And if you look closely at how the software gets built, what developers do when they want to use the kernel, say they're making a new IoT device, is they go to the kernel source code, and then before they even compile it, they have to tell the build system, what configuration do you want? And this can be everything from, well, I want to build for ARM, or I want to build for x86. I want memory management. I don't want memory management. I want USB support. And there are just thousands of these choices that developers can make in order to design a custom version of their kernel without having to reprogram the thing. And so there are kind of default and starting points in the configuration that developers will tweak. But at the end of the day, the build system is this piece of software that takes in configuration options, enables and disables, so that you can enable and disable them, and then passes those options to the build system, which is separate from the actual C code implementation of the kernel. And that build system selects some subset of the code. It selects some pieces of the code base, which then gets compiled into your custom binary for your router or for your IoT device. And so that build system, that's why the build system is so large and so sophisticated, and why it's its own software product in its own right, because it has to manage all of this variation and has to support all of the many ways that the kernel gets used. The problem with this, though, and why this ties into vulnerabilities in the software ecosystem, is that if you want to actually try to maintain this thing, you want to say, test your software, everyone should be testing their software. Because there are so many variations, it's basically impossible to run a test suite on every possible version of the kernel that anyone could create. And now, not developers don't use every possible version of the kernel, but there are still hundreds or thousands of different variations of the kernel, and the kernel's changing over time. The kernel has an extremely active code base. It's 30,000 mailing list messages per month, 6,000 commits, hundreds of commits a day. And so even if you could kind of enumerate all of the commonly used configurations, well, you got to do that every day for all the change that's happening every day. So to look at the current state of testing of this kernel, this is on the left here. This is a list of the top bug reporters. This is a little old. It's from a couple of years ago, but roughly these bug reporters are usually in the top 10. And so the top two, some of the biggest efforts to test this kernel, is Intel's zero-day kernel test robot and Google's Syspot. And there's others. There's like the Hulk robot from, I think, Huawei. And there are lots of individuals who report bugs and make patches. But in terms of automated testing, these are two of the really big players in automated testing. And if we look at how they handle configurability, they're very good at testing. So the syscaller fuzzer is incredibly good at finding bugs. So it's found thousands in just less than a decade, of like 7 years of running. And Intel 0 Days just reports tons and tons of vulnerabilities that are bugs, and including vulnerabilities. They test all aspects of the system: performance, bootability, build tests, static tests, dynamic tests. But what's kind of interesting here is that this build system, this complex build system, actually causes blind spots in testing because it's so hard to figure out which piece of the code is actually being built. Well, if you've got a bug somewhere in your code that was introduced by someone in your code, but you're only testing another piece of the kernel and your build system is not turning on the vulnerable part, well, that bug, not only will you not be able to test it, it won't even be in the binary. It won't even exist in the code that you're testing. And so there's a real potential here for huge amounts of vulnerabilities in the code that's not being tested, and that just can't feasibly be tested without considering how this software ecosystem interacts with the source code. And so this kind of observation is really what is driving us to figure out how we can improve testing approaches, whether they're static or dynamic, so that we don't have these blind spots, so we can actually see the whole code base. And there has been prior studies by others who have shown that there are these kinds of configuration or build system hidden bugs that have appeared in the kernel and in other software, including critical ones. And so to dig into why a little bit these testing approaches miss so much of the code, let's take a look. This is a table that we studied how configurations turn on and off code. And if we take the default configuration, which is something that, say, syscaller or these fuzz testers base their configurations on, and we look at the set of patches from the last year, for instance, most of those patches are not being compiled into the binary. And so, fuzzers, they have to find a path to new code. They have to find vulnerabilities. But even if it's the best coverage guided fuzzer that can actually reach all that code, if it's not in the binary, it's never getting tested. The testing tools are completely blind to it. And this is just for patches. I mean, if the default configuration turns on, a small fraction of the entire 20 million line code base. So what Intel 0 Day does, Intel 0 Day's kernel test robot, they're a little more clever. They also, they're not doing fuzzing, so they don't have to run for 12 hours or several days. So they'll do random configuration testing. They'll just randomly pick configurations and run some of their tests on it, their build tests, their performance tests. They'll try to randomly build them, boot them, and see if they can find issues with them. But if you take any one given random config file, well, you're not really covering many more of the changes in the code. So if there's tons of new development going on in one part of the kernel and the random configuration file doesn't turn it on, then it's not being tested, at least not automatically. Maintainers may be testing it, but they're at least not being seen by these robots. There is a way to try to turn on as much of the kernel as you can. So there's this all yes config, or the maximal configuration file. And this does cover most of the patches. The problem is that all yes config is not really suitable for actually runtime testing. So for one thing, it takes 10 times longer to build. So it's hours instead of minutes to build, at least on commodity hardware, building in sequentially. And they're not really designed for runtime testing. So it makes a gigantic binary that has code from multiple architectures. It has devices that may not be relevant. And it also just has no variation. So it's a single version of the kernel. And if there's some combination of configurations or some piece of code that's being missed, it'll never be tested. And so test robots don't really rely on maximal configurations for much, except for, say, build testing. That's mostly what it's designed for, to make sure that code actually passes through the compiler. And even then, as we found in our work, lots of build errors are missed because it's only one variation of the kernel. So test robots mostly rely on these two approaches: having a fixed default configuration or doing random testing. And so just to highlight again where maximal testing is used, syscaller doesn't even use all ESConfig. They base their kernel on the default configuration because they want, it's a fuzz tester. They want high throughput. They want fast tests. And Intel 0 Day really only uses it for build testing. So most of their test suite does not get run on the maximal configuration. So one of the key problems here, and there's lots of things to address here, but one of the key problems is there's just lots of ways to pick your configuration file to build for testing. But currently there was no way to guarantee that changes that you're actually committing to the kernel are actually getting built.
Hello, Dr. Paul. Can you hear me? Hello, Dr. Paul. Can you hear me?
Are you able to hear me? So my my machine crashed actually. So
Okay.
I'll continue on a different device.
Yes, please. But we can still see your screen.
Are you able to hear me?
Yes.
Okay. I can't hear you though.
Oh, can you hear me now?
And I guess my zombie account is still trying to screen share even though the machine died. Are you able to stop that? Because I
Yes,
can't screen share
I
on
can
this
stop that.
machine.
Does that help? Can you share now, Dr. Paul?
Okay. So I think you can hear me. You can see my screen. So I'll just commence here. Let me. So to try to continue where I left off, apologies for that. My machine actually just crashed, surprisingly. That's the worst time to crash. But the main key here is that there's lots of ways to select configuration files, but no guarantee that the code you're actually changing that you actually want to test is getting built. So these test robots, they're meant for continuous integration testing. So they're meant to be testing the kernel as it's changing. So the approach that we have come up with is to look at the whole space of configuration testing tools. And there are lots, and they're all great tools. They all have their own purposes for testing. So ranconfig is meant to just give you random configuration files, defconfig, a default one. There are maximal configuration testing tools like Vampire, which go beyond all ESConfig to make an even bigger kernel. And there are combinatorial testing approaches that try to test lots of different combinations of configuration options. And these are all great for exercising different variations of the kernel. But none of them address this problem of patch coverage, of actually trying to build changes as they come in to a code base. And so this is just a graph that shows build time, which is kind of a proxy for how fast the fuzzer will run or how long it'll take to build, versus patch coverage. And so tools that require doing lots of configuration files, well, their build time is going to be a lot slower because you have to build a lot of them in order to test lots of variations. And they may not even cover the patches you want. And the trade-off is having lots of patch coverage by having a big configuration file, but then your build time is going to blow up. And you may not even be able to produce a runnable or loadable kernel in that case. So our approach, and one of the main things I want to talk about today, is this technique we came up with called K-repair. So in order to understand what K-repair does, let me dig into the build system, the Linux kernel build system. And this is very common to most C-based build systems. So there's some input to the build system, some set of configuration settings. And the build system takes those and then produces your binary, produces your variation. So inside here, there are several common tools that are used. There's, in the Linux kernel, there's kconfig. Kconfig is a description of all of the configuration options and also constraints on valid ones. So this is where developers can say, don't turn on USB file systems unless you have the USB subsystem turned on. So this is just avoiding invalid builds of the kernel. In simpler software, this might just be a text file saying, hey, turn these options on, don't use these options together. The kernel has an automated way to do this. And then there's make files, which a lot of C-based systems use. And these take the configuration options and determine which files to compile, which parts, which compilation units, which pieces of the kernel to actually compile and build. And the third piece of this, at least for build configuration, is the C preprocessor. So these are your pound if defs, end ifs. These are slicing out individual lines of code within a C file. And these pieces together are what basically implement the configuration. The build system takes which options you want, and then there's just a gigantic set of condition checking to see which parts of the source code that you need to include in order to compile this kernel. And then finally, the compiler and linker takes the resulting source code and produces the binary. So we just look at the part of this that selects source code, because this is the part that is relevant to how we can pick recently changed code or pick code for testing. These are the pieces that are involved in this. So in our approach, our idea is to treat the build system like a piece of software, and then use program analysis techniques in order to glean information from it, just like, say, a compiler would for optimization, glean information from it and use that to help guide the testing tools into picking the right configurations, or at least better configurations that will give them a better chance of hitting the code that's being changed in the kernel. And so the way K-repair works is it takes some old configuration file, like let's say it takes syscaller's existing configuration file. It takes the code of interest that we want to build, and then it gives a new configuration file to syscaller and says, hey, if you use this one, you may not be guaranteed to touch that code, but at least you won't have changed code omitted from your binary. You're going to have that code in your binary. And then you can just drop in this configuration file to the existing test infrastructure. So nothing about the test infrastructure has to change at all. You can just drop this in as a replacement. And our hypothesis is that we'll get better test coverage of actually changed code, and ideally more bugs and different bugs found. So here's how this works. We take these three pieces of the build system, and we've got a suite of program analysis tools that analyze the code of each of these pieces of tools. So treating these as if they are like programs, just like a C program, even though they may be written in these custom domain-specific languages, like make files are written in make. Kconfig has its own language. The C preprocessor is not the C language, it's a different language. But we treat them like program code, and we analyze them so that we can automatically discover their behavior. So we can figure out how they are picking pieces of code from the configuration settings. And if we can figure out how they're picking code, then we can kind of invert the build system. We can take, instead of taking a configuration file and the build system figuring out which lines of code to build, we can take lines of code and say, okay, which configuration files will actually turn on that line of code? And so if we could solve that problem, then we have some chance of providing better configuration testing options to testing tools, to test robots. So let me dig in a little bit and to show you how this works. So CAREER's algorithm works in 3 steps. First, the program analysis step. We figure out which constraints in these build system tools are relevant to covering patches. So we try to see how these build system tools are involved in covering certain lines of code. And then we take the old configuration file and remove options that are in the way of this coverage, that are mutually exclusive with this coverage, that are causing logical unsatisfiability. And then we have the repair step, which re-adds settings to make a full configuration file that will ensure that we will cover these patch coverage constraints. Here's what that looks like diagrammatically. So the first step is figuring out these configuration coverage constraints. And so we use a solving tool, an automated theorem prover that's used commonly in a lot of program analysis tools called Z3. It's a satisfiability solver. And our tools will analyze the build system code and produce constraints that say, if this constraint is true, then this piece of code will be covered. And so once we have that, we can use those constraints in order to figure out which parts of the configuration file are standing in the way of patch coverage. And that gives us this reduced configuration file. And then finally, we do the repair step, where we add back options using the constraints to guide us into which options that we should be turning on in order to actually cover these patch constraints. So the key evaluation question is, does this work? Can we actually get the kind of coverage that maximal build configurations have, but still be able to build quickly and run fuzzers on them and load them? And so one of the main tests we did was to compare the 2 extremes. We took default configuration files here on the bottom left, which cover very little patches. So this is the kind of configuration file that Syscaller and other testing tools use. They build very quickly, but they cover very little code. And so they often miss patches. And so here we have 2 axes. We have the x-axis is the % patch coverage on average, and the y-axis is build time. So how fast this configuration file can build the binary. And so at the 2 extremes, we have the default configuration file, which builds really fast, but has very low patch coverage. And we have the maximal or all yes config file, which covers lots and lots of patches, but takes a very long time to build, and also just may not be something that's actually bootable or runnable for, say, Syscaller. And CAREER here on the bottom right is kind of the Goldilocks solution. We get the kind of fast building kernels that defconfig has that are still compatible with testing tools like Syscaller, but they build really fast, and they actually will build and boot and run with testing platforms, unlike a maximal configuration file. So there's a lot more information in the paper. This is like hot off the presses. We just made the camera ready for a paper on this. It's going to be presented hopefully by Najib, who was the first author, PhD student just graduated at FSC 2024 in the summer. But the paper is now available online if you'd like to take a look more into detail. We also test the performance of this, how fast it is. We test random configuration files, and we actually find some build errors and report these to the kernel developers who accepted, some of our reports. So it turns out that even build errors can be found just by modifying the configuration file. So the next step to this, what we're working on now, is to actually apply this to the test robots. So one of our big focuses here is to take Syscaller, this fuzz tool, and to see if using this guided configuration selection approach will actually improve Syscaller. And our initial studies show that it indeed does. So this Venn diagram shows new bugs found by Syscaller in the green bubble on the right. And confuzz is our improved fuzzer, which does better configuration selection before fuzzing. And we find several times more new bugs. So it turns out that they find a similar amount of alarms overall. But by mutating the configuration file in this way and actually ensuring that we cover recent code, we're actually able to find new bugs. Now, some of these bugs are related to the new code, some of them are not. We're still investigating why this happens. But the results are there. We actually see that just mutating the configuration file provides pretty dramatically different results on the behavior of the fuzzer. So we're still investigating why, but we've got some good results, initial results so far, including one CVE that was reported by my student Sanan, who found, a security relevant crash that had not been found before, but was not even recently added to the kernel. So this tooling, this CAREER tooling, can be found online in CAREER. And so let me wrap up here by talking about some of the other directions we have in our lab. So this is not the only approach we have. So this is just helping testing, but we're also looking a lot at static analysis. So can we improve static analysis tools so that they know about the build system and can handle all variations of the code at the same time? We've also analyzed the build system code itself for bugs. So it turns out that there are opportunities to make mistakes in writing the build system. And so we've got a tool called Kismet, which is now integrated into Intel zero-day kernel test robot that reports a lot of this. So here's a bug report from Intel zero-day, which one of the developers is saying, hey, I thought I got this configuration file right, but or this configuration specification right, but this tool was able to actually warn them about some of these configuration bugs. And so, that paper is also available. That paper is from a couple of years ago, but I'll give you a link to the website where you can see that work. And of course, we're looking at improving fuzz testing and also just translating away from C, helping the process of moving away from memory unsafe languages to memory safe languages. So here, I'd like to thank the students who are working on this work. So Najib did the CAREER work and Jeho. Brent is working on automated translation. He also has a paper this year at ICSE on automatic translation away from unsafe languages. And Sanan is working on fuzzing, and who actually found a vulnerability from applying these testing approaches. So that's all I have today. Thank you so much for your time. And please go to this website if you'd like to see more papers, tools. And I'm happy to take any questions you might have.
Great. Thank you so much for your presentation, Dr. Paul. So we have some questions. So the first one is thanks for the great presentation. As you know, NVIDIA sees the future of coding as a career might already be dead. So what do you think about this from the perspective of software testing and engineering? Will the future bring vulnerabilities that may appear because of the lack of human knowledge and the dominance of AI in coding?
I would say so. So I don't really have expertise in this. I mean, I certainly think kind of personally, are there going to be engineers who, need to learn this kind of algorithmic programming? I guess currently there's kind of a bootstrapping problem though, right? Like those AI systems are built, or at least currently, with traditional software engineering. They're maintained with them. So I guess at some point, maybe the bootstrapping problem, like they can write themselves and develop themselves. If that happens, then certainly, then you'd have fully autonomous development, I guess. But I don't think we're there yet. And there's still a lot of efforts. And actually this configurability is a little related to AI. There are researchers who are looking at, these machines are highly parameterized. There's a lot of choices in how you design architectures. And so there is research actually on the configurability of AI itself. But to whether development will, engineering, software engineering will exist, I don't know. I guess that could be in any engineering, right? I mean, you could imagine AI saying, well, we're going to build an airplane for you, design a bridge. I think software engineers' jobs are safe, at least for a little while. I don't think it'll be happening, next year or something.
Okay, great. Also, you had shown us your GitHub repository.
Oh, yeah.
Like open source and people can contribute to that now?
Absolutely, yeah. It's free and open, free Libra open source software. I think it's GPL2. So feel free to use it. Send issues. If you'd like to fork it and use it, or if there's something you'd like to work on or any feature, I can't promise I'll have time to do it, but if we are trying to add features as we go along. But trying to do research and maintaining software is it's a challenge. We try to make them production ready, maybe like beta level ready. But the Intel kernel test robot is running that one of our tools, so we try to be pretty careful about development. But yes, free and open source. Go to the GitHub page, download it, use it.
Great. So we have another question. Is KeyPair something that could be deployed as a downloadable scanner on personal devices?
KRepair?
KRepair, sorry.
Yeah, I mean, right now it's targeting the build part. So I had that diagram of all the phases of the software. We're focusing on the build system right now. That's like deployed software, kind of monitoring software. We are looking at that a little bit. So I have a colleague, Shui-Chang Wang, who is working a lot on software system security, who actually is looking more at like deployments, trying to find privacy or security vulnerabilities in deployed software. And so we're trying to collaborate on something with the software supply chain, which is also becoming of interest nationally. But KRepair, no, I mean, it's really just a tool for the Linux build system. Wouldn't help you on a deployed system.
All right. So great. Thank you so much, Dr. Paul, for this wonderful presentation. So for your time, we will be sending you a plaque and a certificate signed by our dean. So
thank you. Okay.
Conclude at this webinar. Thank you so much.
All right. Thank you.